Hello everyone, this is Yijing. I hope you enjoyed our skip week because of snow. The class we missed last week is our first workshop about solutes, solutions, and osmolarity, which in my opinion is a very important one because the following several labs and workshops are related to this one. We can't seem to be able to find a common time that's available for everyone to make up for the class. That's why we decided to combine the first workshop and lab 2 together into this week's class. Then I figured the time during class will be very limited. You won't have enough time to thoroughly understand the new information contained in the first workshop, and it does contain a lot of new information. That's why I decided to make this series of videos for you to watch at the time of your own convenience, and also for you to have something to review with if you want to look back. Okay, the topic of the first workshop is the importance of water, solutes, solutions, and osmolarity. Let's first look at the 6 learning benchmarks that I made for you to review with. The first one is you should know how to calculate osmolarity and osmolality. Second one, you should learn how to make a solution with a certain osmolarity or osmolality. Third one, how to calculate the overall osmolarity or osmolality of a mixed solution. The fourth one is when you have a percentage solution, you should know how to convert it into osmolality or osmolarity from the percentage. Okay, the fifth one, when you have 2 solutions, you should be able to tell which one is hypo, hyper, or isoosmotic to the other solution, similar to hyper, hypo, isotonic solutions. The last one is to learn how to predict ion and water movements across a semipermeable membrane. Ion movements across a semipermeable membrane is also called a diffusion. Water movements are also called osmosis. This one is the most essential one for this workshop and is the most difficult one. The 6 learning benchmarks are designed for you to have a list to review with. So after the whole workshop, after you watched the whole series of videos, please come back to this specific slide and make sure that you really understand all 6 of them. I believe there is a watermark at left bottom corner of the video, which comes from the software that I'm using to make the video. Please ignore that. Okay, let's move on to the first 2 concepts that we're going to look at today. The first one is called diffusion. Diffusion refers to the net movement of particles from a high particle concentration region to a low particle concentration region. Note that every time when I refer to the direction of diffusion, I'll say high particle concentration to low particle concentration. So particle concentration is very different from overall concentration of a solution, which means if we want to know the diffusion direction of a specific particle, you should only look at the particle itself, not the overall concentration of the solution. Let's look at one example. It's a very simple example. When we have 2 solutions, solution A and solution B, connected with a semipermeable membrane. In solution A, you have 1 molar of NaCl, 1 molar of KCl. And in solution B, you have 2 molar of NaCl. The capital M here is a unit. That's a short form of moles per liter. Is a unit of molarity. Okay. In this scenario, if we want to know the direction of diffusion of sodium ion, does it move from solution A to solution B or solution A to solution B to sodium A? we don't have to look at the overall concentration of A and B. We don't have to compare them. We can just focus on the concentration of sodium ion itself. In solution A, you can see that we have 1 molar, which means 1 mole per liter of sodium ion. In solution B, we have 2 molar of sodium ion, which means sodium ion has a high concentration in solution B compared to in solution A. So the direction of diffusion of sodium ion is from B to A. Another example would be the potassium ion. In solution A, you have a 1 molar concentration of potassium ion. In solution B, you have none. So the direction of potassium ion is from A to B. So in this case, you can see, despite the fact that solution A and solution B have a same overall concentration, but they still have a net diffusion of different ions. The second concept today is osmosis. Osmosis is a special type of diffusion. It refers to the movement of water from a region of high water concentration to a region of low water concentration. Or you can say the direction of osmosis is from a region of low solute concentration to a region of high solute concentration. Here, the solute concentration doesn't refer to any specific solute. Instead, it refers to the overall solute concentration. Let's go back to the previous example of solution A and solution B. You can see that solution A and solution B are composed of different solutes, but they have the same overall concentration. So we say that between solution A and solution B, there's no net water movements. There will be water movements across the semipermeable membrane, but there's no net water movements. Okay? So in this case, solution A and solution B, there is diffusion of sodium ion from B to A. There is a diffusion of potassium ion from A to B. There's no diffusion of chloride ion because they both have 2 molar of concentration in solution A and solution B. And there's no net water movement. There's no osmosis because they have same water concentration or the same overall solute concentrations. Okay. Diffusions and osmosis are also very important to maintain a certain cell volume in organisms. For example, if we have a red blood cell and if it loses some water, causing the cell volume to decrease, causing it to shrink, we call this process crenation. On the contrary, if the water comes into the red blood cells and causing the red blood cells to burst, this process, we call it hemolysis. That's why it is very important for organisms or cells to maintain a certain level of diffusion and osmosis so that it'll be able to carry out normal activity and regular functions. Since we mentioned that the direction of osmosis is from a low overall solute concentration to a high overall solute concentration, we need to know what is the way that we use to express the solute concentrations so that we can make the prediction of the direction of osmosis. Here, I listed several very important ways to express the solute concentrations of a solution. The four ways above the lines are the ones that you may already know. The first one is molarity. Molarity, from the unit, you can see that it means how many moles of solutes do you have in 1 liter of solution. And the second one is weight per volume. It is expressed as grams per liter. It means how many grams of solutes do you have in per liter of solution. And the third one is mass percentage solutions. When you have a solute that is in a solid status in room temperature, and when you dissolve the solute in water, you can express the solution, the concentration of solution in this way, the mass percentage way. So you just use the weight of solute over the weight of the solution, and then you multiply the result, the ratio, by 100% to get the mass percentage solutions. For example, for the physical saline, you have 0.9% of saline solutions. The last one, molality. Molality is very similar to molarity. The difference between molarity and molality is in the denominator. For molarity, they have the denominator as per liter of solution. But in molality, the denominator, not only the unit is different, but also the part of solution that they're referring to is different as well. So in molality, instead of having per liter of solution, they have 1 kilogram of solvent. The two ways to express the concentration of solutions under the line are osmolarity and osmolality. From the name, you can tell that osmolarity comes from molarity and osmolality comes from osmolality. That's very true. And the difference between these two concepts are only in their denominators. So let's look at molarity for review first. Molarity equals to how many moles that you have in a certain solution over the volume of a solution in the unit of liter. Okay, let's take the first question in workshop 1 as an example. Workshop question 1, how do you make 1 liter of 2 molar NaCl solution? Again, the capital M here is also referring to unit of molarity. It's the same, it's a short form for moles per liter. So every time when you see a capital M, that's moles per liter. That's a unit for molarity. Okay, in order for us to know how to make a certain solution, we need to know two things. One is the volume of the solution. The second is the weight of the solutes needed to make the solution. So in this question, the volume of the solution is already given as 1 liter. So the only information we need to find out is the weight of NaCl in the unit of gram to make the solution. Okay, so here I give you a calculation process. You can see that when you have 2 molar of NaCl solutions, which is 2 moles per liter, it's like you have 2 moles of NaCl in 1 liter of water. In 1 liter of solution. So all the water here should be changed to solutions. Okay. When you have 2 molar NaCl solution, that's like you have 2 moles of NaCl in 1 liter of solution. What a coincidence. You are asked to make a 1 liter of NaCl solution, so you just have to find out what is the weight of NaCl for 2 moles of NaCl. right? In order for you to convert from moles of NaCl to grams of NaCl, you just have to multiply the moles of NaCl by its molecular weight in the unit of gram per mole. Okay, so we use 2 mole to multiply that number by the molecular weight of NaCl to get the grams of NaCl, which is 117 grams of NaCl. That's in 1 liter of solution. So if we want to make 1 liter of solution, we should put in 117 gram of NaCl. If you happen that's a coincidence that the question is asking you to make 1 liter of solutions. But if it asks you to make 2 liters of solutions or 3 liters of solutions, you just multiply the volume of the solutions by this number to get the final weight of NaCl needed to make the certain solution, right? Okay, so the final answer is you need 117 gram of NaCl and dissolve it in a small amount of water in a beaker, and then transfer the dissolved amount of solution into a graduate cylinder. Add enough amount of water to a total of 1 liter. Does that make sense to you? So that's a description of the process of how to make a certain solution. Okay, I'll repeat again. When you already know that 117 gram is the weight that you need to make the solution, you can't just simply combine 117 gram of NaCl with 1 liter of water, because the 1 liter is not only water. Is the total solution. So for you to make the solution more precisely, the process should be described in this way. We put 117 gram of NaCl with a small amount of water and dissolve them thoroughly in a beaker. And then we transfer the small amount of solution into a graduate cylinder. And then we add enough amount of water into the graduate cylinder to make a total volume of 1 liter solution. That's the whole description of how to make the solution. Okay, let's move on to molality. The unit for molality is moles per kilogram of solvent instead of solution is per kilogram of solvent. That's something that you really should pay attention when you do the calculations of molality. So the short form for the unit of molality is molal. You should notice that molarity is used much more commonly than molality. But the calculation method for molarity and molality should be very similar. You just have to pay more attention to the denominator. Instead of per unit of solution, you should use per kilogram of solvent for the calculation of molality. Today's topic is about osmolarity and osmolality. From the name of osmolarity and osmolality, you can tell that they are closely related to the process of osmosis. That's true. If you still remember, the direction of osmosis is from high water concentration to low water concentration. Or you can say the direction of osmosis is from low solute concentration to high overall solute concentration. So how are we going to evaluate the water concentration or overall solute concentration in a solution? That's where osmolarity and osmolality comes into hand. Let's go back to the previous example, solution A and solution B. When you have 1 molar of NaCl, 1 molar of KCl in solution A, and you have 2 molar of NaCl in solution B. They are connected with a semi-permeable membrane. The NaCl and KCl molecules, when they dissolve in water, they don't maintain as molecule status. Instead, they dissociate into different ions. In these 2 solutions, we have Na ions, chloride ions, and potassium ions. These ions, they are in constantly random motions. So, for example, the 3 types of ions in the left side, in the solution A, they're in constantly moving motions. So they're sort of knocking the semi-permeable membrane between solution A and solution B. And that is the driving force of osmotic pressure. That's causing the process of osmosis. The reason why there's net water movement between a semi-permeable membrane is because the osmotic pressure between the 2 sides of a semi-permeable membrane is imbalance. So in order for the osmotic pressure between the 2 sides reach an equilibrium, there will be a net water movement. So the water will move to a higher osmotic pressure part in order for the 2 solutions to have a balance, to reach an equilibrium. Knowing that, we can understand that the osmotic pressure of a solution is directly related to the number of actively moving particles residing in this solution. Okay. For example, when you have 1 molar of NaCl molecules, instead of 1 molar of NaCl molecule, when they dissolve into water, you have 2 molar of actively moving particles from this molecule. And then you have 2 molar of actively moving particles from KCl in solution A. So in a total, you have 4 molar of actively moving particles in solution A. That's the that's the osmotic pressure that's related to solution A. And to solution B, we have 2 molar of NaCl. That's like 4 molar of actively moving particles. So you have 4 molars of actively moving particles in A, you have 4 molars of actively moving particles in B. We know that they both have the same osmotic pressure, so there's no net water movement between solution A and solution B. There's no osmosis. So if we want to quantify the number of actively moving particles, how are we going to do that? Let's say instead of a perfect 2 actively moving particles that 1 molecule of NaCl will give, it actually gives 1.8 because some part of the NaCl molecules will still remain as a molecule status, right? Okay, so let's say 1 part of NaCl molecule is going to give out slightly less than 2 parts of actively moving particles. And this number of particles that 1 molecule can give out, we call it a dissociation constant. So for NaCl and KCl, they should both have a dissociation constant that is slightly lower than 2. Okay, so we have the osmolality and osmolarity definitions as this. Osmolarity equals molarity times dissociation constant of this molecule. Similarly, we have osmolality equals molality times dissociation constant. And we can use osmolarity and osmolality to express the concentration of the overall concentration of a solution when it comes to the direction of osmosis. And it makes sense because Osmolarity and osmolality, they are describing the number of actively moving particles in one solution, and that is directly related to the osmotic pressure, which is the driving force of osmosis, the net water movement. Now that we have the set of definitions of osmolarity and osmolality to express the overall concentrations of a specific solution that is related to the osmotic pressure or osmosis, we can safely say that the direction of osmosis or the direction of net water movement is from a lower osmolarity to a higher osmolarity solution. As a comparison, the definition between osmolarity and molarity is very different. You should notice that when we define osmolarity, we don't care what type of molecules, what type of actively moving particles there are in a contribution of the total amount of osmolarity, right? For example, when you have solution A of a mixture of 1 molar of NaCl and 1 molar of KCl, you can simply calculate the osmolarity of NaCl, which is 2 osmolar, and the osmolarity of KCl, which is 2 osmolar, and add them up together to have a total of 4 osmolar as the osmolarity of solution A. So for osmolarity, we don't care what type of molecules are contributing to the total value, which makes sense because in the definition of osmolarity, we only care about the amount of osmotic pressure that these solution is holding, right? No matter if it's a sodium ion or chloride ion or potassium ion, the osmotic pressure provided by one actively moving particle is always going to be the same. So in the definition of osmolarity, we only care about the amount of actively moving particles there are in a solution instead of the type of actively moving particles. This part is very different from the definition of molarity. When you have a mixture of 1 molar of NaCl, 1 molar of KCl in solution A, you can simply add them up to have a 2 molar of mixture solution. If you say that you have a 2 molar of NaCl and KCl solution mixture, that doesn't make sense, right? Because the definition of molarity is designed for you to understand the composition of a solution. This type of properties of a solution that is discriminative about the types of molecules that are contributing to the property, and only cares about the amount of molecules that are in a solution is called colligative properties. It spells as colligative properties. There are only 4 colligative properties of a solution. If you're interested, you can look it up. And that is all to the background part of our workshop 1. Let's make a very brief conclusion. So we covered the definition of osmosis, diffusion, and you should also know the direction of diffusion of a specific particle and the direction of osmosis between 2 solutions.